So problem 7a is discussing the Boltzmann equation and entropy. So again, there's a great little description about the Boltzmann equation that I'd like to read. It says, on a microscopic level, the entropy of a system increases with the number of available microstates, which are the possible arrangements of the positions and kinetic energies of the particles in the system. These states cannot be examined individually, but are instead studied by using statistical analysis. Each thermodynamic system has a unique number of microstates associated with it, designated W. Entropy increases with the number of microstates. So entropy is the randomness and disorder of the environment. So a good way that I like to think about entropy that really kind of helped me wrap my brain around it is the world is heading toward increased entropy. So if you have a glass and you break it, and you drop it on the floor, it's going to shatter, okay? The glass is heading toward increased entropy. So it's one solid piece of glass. You drop the glass on the floor, it shatters into a million teeny tiny pieces that you then have to clean up. It's heading toward increased entropy. That glass is never going to come back together. So the universe is always heading toward increased entropy. So what this little paragraph is basically saying is an increase in microstates, designated W, is associated with an increase in entropy, S, which is known as an increase in disorder. And some ways that you can increase the entropy, when we talk about increasing S, you can increase the volume, so there's more area for molecules to move around and become disordered. You can increase the temperature. So by increasing the temperature, you're increasing the kinetic energy of the molecules. They're hitting against each other more frequently. That's causing a lot of disorder. And you can increase N, the number of moles of the gas. That's also going to cause more disorder. There's more molecules hanging around. So this problem says to consider a system consisting of a cylinder with a movable piston containing 10 to the 6th gas molecules, 298 degrees Kelvin at a volume of 1 liter. Consider the following descriptions of the system. So basically, we're going to go through and see what's going on with each of these parts and see how entropy is changing with these new environments. So the initial system. So there's no change there. So if you start with the initial system, the volume of the container is changed to 2 liters and the temperature to 395 Kelvin. So in B, you're increasing the volume and increasing the temperature. So you're definitely increasing the entropy and increasing the number of microstates. Starting from the initial system, a combination reaction occurs at a constant volume and temperature. So a combination reaction is going to be a reaction where you take 2 reactants and form one product. So if you take A plus B and you form C. So you're going from a more disordered state to a less disordered state. So in this one, you're actually going to decrease entropy. Okay, so D, we start from the initial system. The gas reacts completely to produce 10 to the 7 gas molecules, so more gas molecules at 395 Kelvin, so at a higher temperature and a volume of 2 liters. So you've increased N, you've increased T, and you've increased V. Now the final one, E, starting from the initial system, the temperature is changed to 395 degrees Kelvin at a constant volume. So in E, you're only increasing the temperature. So now it's going to ask us to arrange the descriptions in the order of the increasing number of microstates in the resulting system. So if you look at A through E, you see we have a varying number of changes. Either no change, a decrease in entropy, one thing happens, 2 things happen, a couple of things happen. So we're just going to arrange these in the order of increasing number of microstates. So we're going to start with the least number of microstates, because the least number of microstates increase as a decrease in entropy. So when we change temperature, volume, moles of gas, that's causing the most change in entropy. So, to start with the fewest number of microstates, that would be C. So in C, you're decreasing the number of the amount of entropy. The next increasing number of microstates is going to be A, so no change from the initial system, whereas in C, you're changing the initial system and decreasing the number of gas molecules. The next increasing number of microstates is going to be E. We only have one factor that's changing the entropy, and that's an increase in temperature. The next one will be B. That's going to be two factors that cause an increase in entropy, the volume and the temperature. And then finally, the option with the most increase in microstates is going to be D, since we have three factors that increase the entropy: the moles of gas, the temperature, and the volume.